Learn how to develop a Kalman filter on embedded C++ platforms such as Arduino or ESP32 microcontrollers. You will learn how to develop matrix operations for Kalman filtering. So we have our system here with our parameters. We have 4 states and 2 outputs. The initial Kalman filter conditions are shown over here for the error covariance, process, and measurement noise. Let's dive into it. Let's now go over the Kalman filter equations. We have 4 states and 2 outputs, so n and p is equal to 4 and 2 respectively. Beginning with your system step, you have x at the time step k plus 1 is equal to a times xk. Your system matrix is given by a. Then y is equal to h times xk. Your outputs are y. Since we have 4 states and 2 outputs, x will be 4 times 1 and y will be 2 times 1 respectively. For your Kalman filter prediction, you have to get the error covariance p. You have to initialize it first and then update that by doing APA transpose plus q, where the process noise is given by q. In the update step, you have the measurement noise r, and you have to find the Kalman gain by doing ph transpose multiplied by hph transpose plus r inverse. Then you have to get your state estimate updates by doing x hat plus equal to k times y minus h x hat. And then you have to again update your error covariance p by doing I minus kh times p. Since we have 4 states and 2 outputs, a, q, p, and I are 4 by 4, x is 4 by 1, h is 2 by 4, y is 2 by 1, r is 2 by 2, and then k is 4 by 2. This will be very important in defining your system in C++ after. Here are the template functions in C++. So in this case, you will have to use templates because you have to have many different sizes for your arrays. Now, if you look at those equations before, you see that we have a bunch of operations, especially adding, subtracting, assigning, and matrix multiplication. So let's go over these methods step by step. The first one is n times 1 matmul. So that's multiplying a matrix by an array. So x hat is equal to ax. A is a matrix, x is a vector, so you have to multiply it that way. Then we have an n by m matmul, so this will multiply any 2 matrices. The next one is n by 1 addition. Then n by m addition will just add 2 matrices together. N by m subtract will just subtract them, the opposite of the adding operation here. N by 1 assign will just assign a vector to this out vector and then return it. The same thing for the matrix over here. We also have a 2 by 2 inverse. Since we have 2 outputs in the Kalman gain calculation, you have to get the inverse. Then you have subtracting of 2 arrays, n by 1 subtract. Then we have a casting. So now there will be situations where you have to cast. So it means that you have to convert a 4 by 1 into just a 4 row vector array. So you have to do this small operation here where you will just assign each value to this result and then that'll be it. Notice how I'm passing in the result at each time step. It's because I will pass everything by reference. I don't want these functions to return anything, and that is why I have a void over here. In RTOS applications, it is preferred to do that. It's preferred to not have methods return anything. So you have to define the result outside and then pass it in there. And now I will show you my system code where you will see how it's implemented. We have the system class over here. Beginning with the constructor, I just set the value of dt inside it. I have my state matrix A, then A transpose, initial states x naught, states x, outputs y, the output matrix H, and the transpose of H. I defined my A transpose and my H transpose before, because then I don't need to calculate it inside of the step. It's better to have everything defined and avoid as many real-time calculations as you can to save time and memory as well. My Kalman filter attributes are over here. So here I have just basically standard deviations, which I'm just setting over here myself. These parameters must be changed according to what filter performance you want. So SG, SG2, Q, and all the way up to Q3 are just variables which you can change. I have my initial error covariance P0 4x4, which is a diagonal matrix of 0.01. P and K are not defined yet because those will be calculated inside of my Kalman filter prediction and the update step. I have my process noise Q, which is defined as so. My measurement noise R is also defined this way. I have my identity matrix 4x4, which is defined. My initial state estimates X hat prev and then X hat. This will be calculated, so it is not defined yet. I then have all my template methods, which I talked about before. Lastly, I have my step method, which is my system step, the filter prediction, and the update step. Since I'm defining templates, you have to use a .tpp file, not a C++ file. It is a bit different. This template file TPP is the same as a .cpp file, but since I'm using template definitions here in my class, you have to use this one here. Let's look at how this file works and you will see how these methods are actually done. So let's go there. I initialize my sampling time in a member initializer, so I can leave the method body empty. The first one method is n/1 mathmul. So this will multiply an n/1 matrix, an n/n matrix by an m/1 array. So if I have a matrix of size 4x2 and an array of size or 2x1, it'll just do a 4x1 array as the output. So you can see here that it's R1 times C1 multiplied by C1. These two will cancel out and you will end up with just R1. This will multiply two matrices. Now, in this case, you have R2 and C2, R2 CX and CX and C2, because when you multiply this, CX will cancel out and you will end up with R2 times C2 here. So I have more definitions there. And this is just basically doing a simple matrix multiplication. I know that this is not the most optimal way to do it. There are set algorithms for multiplying matrices like Strasson's, or you can also use dynamic programming. But this is just a simple operation, so I don't need to make it very fancy now. This will just multiply matrix 1 by matrix 2 and update the result. Notice how I'm passing in the result by reference, so I don't need to return anything, and that is why this method is wide, and so are all the others. This one does addition, so I'm adding array 1 plus array 2, each element of it from I equals 0 to R1. R1 is the number of rows in the array. We can use the same concept over here for two matrices. If you have matrix 1 and matrix 2, which are the same size, of course, you can add them up across each row and column inside of a loop here. Matrix 1 plus matrix 2. This one is just doing subtraction, so opposite of the addition there. This one just assigns the value of input to output. So I'm passing it out by reference, and then I'm just doing for I equals 0 to R1, just set out equal to n. Same concept for here. In this case, we have an n by n, so it's a square matrix, and I'm assigning the value of in to out across rows R1 and columns R1, which is the same value here. So that's why I have my same template. Here I'm doing a 2x2 inverse. I find a determinant and then get the adjoint and then just set the value there. I do check if it is 0 and then return, because then you don't want an inverse of an infinity. I do casting to double because here I'm doing a double operation there, so that's what you need. It'll set the inverse of matrix 1 to result, and then that's it. Over here, I'm subtracting two arrays of length R1, quite simple. And this one is just doing casting. So this will do an array of size 4x1 or a 4x1 matrix into a 4x1 array. So I'm just assigning the value of input to result. You notice how result is R1, it's just a row vector, and then input is R1 and one column. So I'm just getting rid of my column here. So that is why I'm just doing result I is equal to input I0. That's it. Here's my step. Now think about this very carefully. Why am I doing x naught and x here? So if this was x, imagine what would happen in this matrix multiplication. Let's go up and see what the method is. You know, notice how to multiply matrices, I have to set the result to 0 initially because I'm just multiplying it from scratch. If I set this result to 0 and if I have this matrix over here, these two will both become 0 and that's incorrect. So if I have x here, then when I set this x to 0, this will also become 0 because I'm passing it by a reference. I'm using the pointer. So you have to use a different array2 and result. These two cannot refer to the same memory address. So that's why this should be x naught. And then when I do it, I have to assign x naught to x because I have to update it. Lastly, I can get my states y, which is h times x. So my output's y here. Now this one, I don't need to do any assigning because y, h, and x, they all occupy different addresses in the memory. So you can just normally pass it in. You don't have to worry about any other value being set to 0 by mistake. In my prediction step for the Kalman filter, I'm doing the same thing here. So p equals a times p naught. And because I can't have p here, since these two values of p, they occupy the same memory address, but p naught does not, it occupies a different memory address. I get p and then assign it to p naught, and then I have to do p naught times a transpose because it'll be a p a transpose multiplied, so I have to multiply it separately. And then I just add it to q and then assign p naught to p. I can't add this time because here I'm just doing p is equal to p plus q here, so I don't have to worry about any operations which are on the same memory address. If you still don't understand it, I will leave it to you as a homework. Please look through this code in detail and try and make sense that you will be able to easily understand why I do it this way here. Here's my update step. The first thing I do is get my Kalman gain. Since the Kalman gain method is very long, I break it up into many parts. First I do p times h transpose and then h times p times h transpose like this. I call it sequentially here. I then add it to R. Then I just do an inverse 2 by 2 here. I invert all this I got. I then get my matrix multiplication there, k, k1, k5. So that's my Kalman gain here. And then I can just use that to update my state estimates. So I create a new vector here and then just do a matrix multiplication. And then I can get my state estimate updates. I then do the addition there. And then I just convert it into a 4 by 1. If I hover over, you can see that this is 4 by 1 and that's a 4. So that's what this casting will do. Lastly, I have to update my error covariance p, which is I minus kh times p. So that's why I'm subtracting it here. I minus E1 is k times h, and then just multiplying that by p and then assigning it to p naught. Then the cycle will repeat over and over again. This p naught will go all the way here, and then repeat. So that is it for the definition. Let's look at the testbed. So before you actually use your embedded systems, it is recommended to build a C++ program because you can actually debug in VS Code. When you look at embedded systems, they are hard to debug because they run in real time, they run quite fast. But it's not an IDE, right? Like if you have a microcontroller, you cannot just like stop the microcontroller and debug it. You can, but it is a lot more advanced and you need like special software to like do it. So here I'm just doing a step and then Kalman filter here. So I'm printing out my state and my state estimate. So let's look at that here. For the first 100 steps in time. So I'm just gonna, okay, we have a bunch of values over here. Now initially it's all 0 because my state estimates have not yet updated. Let me actually add another line over here because okay, this should look better now. Let's rerun this here. Okay, now it's a lot better. Let's go all the way up. We have the first 4 is your actual states, and those are your state estimates. So they start off at 0, and then you will see that they will slowly increase. So if I go up a bit here, they are going up. It is a bit slow, but eventually they will catch up. You have to give this more iterations here. So let's give it like 1000, which is about 10 seconds. Okay, now you can see that when the states get to 10, the state estimates get to 6.4 and then 1.2, 1.2 here. So this one does overshoot, and it's all because of the way the filter is tuned. Keep in mind that this filter is not perfectly tuned. I'm just giving you a template here. You have to adjust these parameters and adjust P0, Q, and R to get the filter performance that you want, and it does take a lot of experimentation to do it. But this template should give you a good starting point. You can see that if I step more, so let's step to 1500 here. You can see it's doing well with the first 2, but the last 2 are exceeding because the states are staying the same value, right? It's staying at 1. The speed is staying at 1, but then the estimate will increase because the Kalman gain keeps changing for those 2 values. So what you can do is have a steady state gain for just the speed part and let this update. So then these 2 are hatching up to 15 here. Now you have a Kalman filter template to work with on embedded systems. So now let's move on to the RTOS part. Okay, let's look at this Arduino code step by step. The first thing you have to do is install the FreeRTOS library, which is explained in many other videos, so I won't repeat it here. It's made by Richard Barry. If you look in here, just type in FreeRTOS in the library manager. It's over here, so you can just install it and then include the files that you need. You have to include the system class once again. Be sure to comment out include IO stream because that's not compatible on Arduino, of course. It's all embedded platforms. You make one global variable, which is your system, and I have a task over here. So this task does not return anything. You should not return something from a task, and that's why it's void. You should also have no parameters for now, so it's a void parameter. I have one task for system sim, one for system filter, and then for system results. This will just output the results to my serial monitor. You need to have a task handle, the system sim task, and the get system result task. You also have one for the system filter task. In my setup, I create my serial printing rate, and then I create my task over here by using X task create, system sim, system filter, and get system results. I pass in my task handles accordingly, like that. For now, I've commented out the system filtering, so I do have memory issues on my Arduino because it is the Arduino Uno, so I don't have a lot of space to work with. So for now, I've commented out the filtering parameters and also commented out the prediction and the update step. I just have my step for now. Okay, so let's create the task over here. The first task is your system step. It's an infinite loop. You just keep stepping over and over again. You have to add a delay as well. So it's 400 milliseconds for me. My system filter task for now is commented out because I just have my step going on. So this one will just do the prediction and the update step. So this is another task, and I have a delay here of 800 microseconds. For the get system results, all I do is print out my states and my state estimates. For now, these are commented out, and I add a task delay here. So this is essentially the entire RTOS code. Let's look at this task creation, right? Let's think about which task you want to execute first. You have to actually step first. So you want the system to step first and then filter it out and then get the results. The filtering must occur one step after the system will actually start, right? Because you can't have the filter started before. The sensor always works a little bit after your machine starts to like do something, so that's why the filtering step is the next task, and the last one is the get system results. So for now, since I've commented this out, I just have two tasks over here, so two active ones, and let's run this one. So when I compile it, you already see I was using quite a lot of memory here, so more than 30%. So even though it's a small program, and that's because the Arduino Uno does use limited memory, so you have to use a bigger Arduino board. If I upload that, you can see the states being output there. So the first two states are your position and the last two are your speed. The speed is the same at 1, but the position is moving up here. So this will keep on printing out. Now let's uncomment this out, okay? Let's uncomment all this here. Let's activate the system filtering task, and let's also uncomment your filter methods like that, along with these attributes, of course. And let's uncomment everything in this one, predict and the update step. Okay, so this will obviously keep looping unless I stop it. Okay, let's see what happens now. So if I compile this, oh, what's going on? Think I missed. Okay, yeah, I have to uncomment out this one as well. The filtering task. Okay, you see how we have a lot more memory in use, and the dynamic memory is more than 50%. And now this is not good because, like, obviously our program, like, even though it's not big, the Arduino board itself, the Arduino Uno, you don't have much space to work with, so you will be kind of screwed for memory. But hey, like, it's still compiled, so that's good. But now if I try and run this, if I upload this, I don't actually get any serial printing. It does work, but there is no printing mostly because this memory is too much in use and the serial can't use any more memory, right? So for me, I do have an issue, but if you are testing this on some bigger Arduino, let me know if you're able to get it to work. It should, because it does compile, right? Like, I'm able to get my filtering task to work. So it does run, but it does not show up here because too much of the memory is in use. But this should demonstrate how to use RTOS with Kalman filtering. You basically have a task that does the filtering itself and another task that will access the variables and then print it out to the screen. Since we are not having multiple tasks modify the same variable, we don't have to use like a mutex. The tasks don't activate at the same time. We have a 400 microsecond delay here for each task. This one is 800. So yeah, I'll make more videos on this before. This is just a generic introduction to RTOS and Kalman filtering. There is a lot to learn here. And in the coming videos, I will dive more into RTOS and the cool stuff that you can do with it in relation to mechanical engineering tasks. So I hope to see you soon. Bye.